Hello, everyone. Welcome to Mclean 360. So, in this video, I want to show you um, stresses on oblique axis. All right. So, over here, we have a member. Okay, let's read the question. So, the 1.4 KIP, that is kilopound, load P is supported by two wooden members of uniform cross section that are joined by simple glued scarf splice shown. So we are to determine the normal and shearing stress in the glued splice. All right. So think about this as a complete structure here, and then suddenly there is a cut. Okay. So this cut is actually like a plane which has been um, placed here. So think about something which is originally straight, um, and then there is some sort of inclination. Okay, so now this inclination is what we have here. So to solve the problem, the first thing to do is to sketch the surface. So if I try to sketch the surface, I'm going to get something like this. All right. So something like this. So let's assume that originally it was the shaded portion. You know, the yeah. Let's say originally it was like this, and there is a cut. Okay. Now, one thing we have to be careful about is that we have what we call the normal plane, which is passing through like this. And along this normal plane is the P, which is acting here. Right? Now, when you introduce a cut or a section, you have actually introduced shear force V. All right. And then there is this component of the normal force, but then it is going to be perpendicular to the surface or the section. Interestingly, all the time, the angle between the force, the normal force, and then the shear force should always be 90. Okay. But from the question, it can be seen that the 60 degrees is cut with respect to the vertical. So meaning that this shear force makes an angle 60 degrees. 60 degrees with respect to the the vertical axis. Okay. So now think about this. If I have a whole straight line, then the angle here should be what? So that angle must be, okay, let's check. So 90 plus 60, that is 150. So 180 minus 150 is 30. It tells us that a complete angle here to make 180 will be making this side 30 degrees. All right. Having done this, we can actually place, this into some sort of Cartesian plane. So this is P, and then we can project V here. All right. And then we can also project P here. When we do that, don't forget that always the angle between F and P, F and V is 90. Therefore, P become the hypotenuse. Okay. So people, if you have not been able to do this, you cannot solve the question. And that is why I have taken my time to solve this with you. All right. Some of the textbooks, they go straight forward and solve it. But I want to explain it to you. That's why I'm doing this. All right. So what is cos 30? Cos 30 is going to be adjacent over hypotenuse. Now the hypotenuse is P. So therefore the adjacent is nothing but F. So F divided by hypotenuse, which is P. So we can say that F is P cos 30. All right. And then in terms of sine 30, we can also say that opposite, which is V, divided by hypotenuse, which is P. Therefore, V is P sine 30. All right. So now we know F, and then we know V. Okay. Now the stress, which is the normal stress, will be F divided by A theta. So now A theta is the area of the inclined surface. But how can I get A theta? All right. So, the area, so the area or the original area is given by A naught. That is the original area. And then there was a cut. Okay. So that cut, the angle that the cut makes is theta. So we call the slanted area A theta. Okay. So what is cos theta? Cos theta will be adjacent, which is A naught divided by A theta. In other words, the new area A theta is going to be A naught divided by cos theta. Okay. So now, okay, let's call this equation 1, equation 2, equation 3. So let's put everything together. The normal stress is going to be F over A theta, which is what? So it's going to be F is what? P cos 30. Then divided by A theta, which is A naught divided by cos theta, which is cos 30. All right. So now you may be in doubt that why is it the angle is 30? So watch this. The inclination was with respect to the vertical, which was 60. So this 60 is with respect to the vertical. But the actual area was initially like this. So the inclination of the original area and then the new area, which is the slanted area, is the theta, which is 30. All right. So then the normal stress will be P over A naught cos squared 30, because it's going to be cos 30 multiplied by cos 30. All right. So this is the formula for the normal stress. Again, for the shear stress. So for the shear stress, the shear stress is going to be the shear force divided by the new area. And what is it? So the shearing stress, oh sorry, so the shearing stress is going to be V over A theta. But what is V? From equation 2, V is what? P sine theta, which is what? 30. So V is P sine 30 divided by A naught over cos 30. So in other words, the shear stress will be P over A naught sine 30 cos 30. All right. So we just have to plug the values of P and then A naught. So according to the question, P was what? 1.4 KIP. And then the original area is 3 multiplied by 5, which is 15 inch squared. So P is 1.4 KIP, and then the area is 15. Therefore, so let's calculate the normal stress. It's going to be 1.4 multiplied by 10 to the power 3, which is kilo, divided by the area, which is 15, cos squared 30. So what is it then? It's going to be 1.4 divided by 15 multiplied by 10 raised to the power 3 multiplied by cos 30 squared. And what is that? Oh, so we are going to get 70 psi. Okay. So the imperial version of megapascal is psi. And then the shearing stress is also going to be 1.4 times 10 to the power 3 divided by 15 sine 30 cos 30. And what is that? So it's going to be 1.4 times 10 to the power 3 divided by 15. Then you multiply sine 30 cosine 30. So we get 40.41 psi, and that is the value of the shearing stress. All right. So the problem has been solved. All right. So thank you very much for watching. But in some of the textbooks, they don't do everything like this. They just solve it. So please, when you have a question on oblique as this, try and sketch it. All right. Thank you for watching once more.